Hello and welcome to Chemistry with Dr. Clark. In the video today we'd like to talk about heats of formation and using them to calculate the heat related to a chemical change or a physical change. Alright, so let's talk about the heats of formation. Right here on this first page I've got a table of some sample heats of formation. And if you're talking about a formation reaction, let's say we talk about the carbon dioxide. In order to form carbon dioxide, CO2 gas, the question you have to ask yourself is what elements are required to make carbon dioxide? So if you've got some carbon dioxide, you need to have some carbons, and you're going to have to react with some oxygens, right? These are the elements that come together to make carbon dioxide, to form carbon dioxide. Now, when you talk about the elements, you do have to talk about how they naturally occur in the real world. So if we talk about carbon, carbon out in the world at room temperature likes to be a solid, so this is carbon solid. Oxygen out in the real world likes to be a gas, so this would be a gas. But oxygen out in the real world also likes to come as pairs. It's a diatomic molecule, and so it's not just O, it's an O2. So if you wanted to talk about the formation of carbon dioxide, it would be one carbon solid plus one oxygen gas, an O2 gas, turning into a CO2 gas. And for this particular problem, you can see that it's already pre-balanced, right? You start it with one carbon, you end it with one carbon, you start it with two oxygens, and you end it with two oxygens. Now, the amount of heat that goes with this sort of formation would be right here, right? This would be the delta H of formation minus 393.5 kilojoules. Now, we do like to say that it's kilojoules per mole, so kilojoules per mole, because in this reaction, the most important chemical is the product, right? That's what I'm attempting to form. So when we write these equations, we really like to have one of these. So this is the amount of heat required to form one of them. So it's the amount of heat per mole, right? So it's the amount of heat per mole because you're making one of them. Now what this can lead to is some unusual coefficients. Let's say instead of making carbon dioxide, we wanted to make a carbon monoxide. Well, if you're making a carbon monoxide, you've still got carbons, you've still got oxygens. So I'm going to have a carbon solid reacting with an O2 gas, turning into a carbon monoxide. Now for this particular problem, you can see that it's not balanced, right? You've got one carbon to one carbon, but you have two oxygens versus one oxygen, right? So the oxygens are not conserved. So if you wanted to fix this, under normal circumstances, I'd put a 2 here, because you have two O's, and now you have 2 times an O. This does give you 2 carbons, so you'd have to say 2 carbons. Now we're balanced. Unfortunately, though, the way that I've written this equation, you are not making one of the important chemical, right? The product, the thing that you really want to form, you're making 2. So to get around that, we treat the chemical reaction kind of like a mathematical equation. In the world of math, you're allowed to do anything you want to the two sides as long as you do the same thing to both sides. So same thing here. I can do anything I want to the product side as long as I do the exact same thing to the reactant side. So if I were to divide this by 2, that would turn it into a 1, which is what I want. But it means I would also have to divide this one by 2 and this one by 2. So in the end, oops, let me get a different color marker. I would have one of those. I would have 1/2 of an oxygen gas, and I'd have one of those, which is exactly what I want. Now I can say the delta H of formation would be a minus 110.5 kilojoules, because that's the amount of energy required or associated with that chemical reaction. And I can say that it's per mole because it is for 1 mole of the important chemical. Now, under normal circumstances, when you're asked to balance chemical equations, we tend not to do fractional coefficients, like having 1/2 of an O2 is usually frowned upon. But for this particular case here, it's superseded, like by the fact that we really, really want a 1 right there. Okay, so somebody has done all of these chemical reactions, and they've measured the amount of heat that goes with making these. Now, my table is pretty small, right? If you are looking at this in a textbook or you're doing it in a class somewhere, you'll get tables that are small or large, and they'll contain the chemicals that are important for whatever questions you're going to do. But for virtually everything that you can think of, there is a value of heats of formation. Okay, so let's talk about some practice problems. What I'd like to be able to do is use these heats of formations to predict the amount of energy associated with a chemical reaction. Now, let's talk a bit about the theory in the background before we actually do a chemical reaction, or before we actually do like the particular thing I'm asked for, calculating the heat. The way that you can think of this chemical reaction is, instead of thinking of it as a single step, you can think of it as 2 separate steps, right? Like the way that it's written, it talks about sodium hydroxide reacting with HCl, forming sodium chloride and water. Okay, if you were to label it, this would be a double replacement or double displacement reaction, right? The sodium and the hydrogen have just switched places. But let's say that we want to think of it in terms of formations. Okay, if I wanted to, I could talk about making the products. So let's write my NaCl solid and my H2O gas. I could consider forming them, right? So if I wanted to do a formation reaction, so we'll ignore the real reactants, and let's say we'd like to do it as a formation. Well, if you wanted to form sodium chloride and water, what do you need? Well, I would need some sodium. I would need some chlorines. I would need some hydrogens. And I would need some oxygens, right? If you're going to make sodium chloride, you need sodiums and chlorines. If you're going to make water, you need hydrogens and oxygens. Now, just like I did a minute ago, you have to decide, do they come in pairs? Are they diatomic or are they not? And you do have to tell me if they're solid, liquids, or gases. So sodium does not like to come in pairs. It's not diatomic. And in the real world, at room temperature, it's a solid. The chlorines, the hydrogens, and the oxygens, all 3 of these are diatomic molecules. So this would be a Cl2, an H2, and an O2. And out in the real world, at room temperature, all 3 of these would be gases. So gas, gas, and gas. So if I wanted to, I could ignore this and think of this as a formation reaction. Take the elements and form the first product. Take the elements and form the second product. Now, let's talk about my reactants. In the world of chemical reactions, formation has an opposite. Formation is related to decomposition. Decomposition is when you take a compound and you take it apart and turn it into its elements, right? Formation, you take the elements and put them together. Decomposition, you take the compound apart. So formation is together, decomposition is apart. Well, if I look at just my reactants, I can see that if I were to take this apart, the sodium hydroxide has sodiums. So if I took it apart, I'd get sodium. If I took apart the hydroxide, I'd get oxygens and hydrogens. If I took apart the HCl, I'd get hydrogens and chlorines. Right? I can consider this as a 2-step process. I can consider it as the reactants getting taken apart, then they all get reshuffled and put back together. It's kind of like if you have a building set. Let's say you have a box of Legos. And so the first person in your class, picture yourself, you're back in like grade 1 or grade 2. So if you go into class and they give you this box of Legos and you build something. So you've built this beautiful little plane, okay? Your reactants here, that's like you building the plane. And then you lay your plane back in the box and you hand it to the next person sitting next to you. Well, what they do is they take it all apart and then they put it all together and they make a nice little truck, right? The atoms are like the individual building blocks. In the beginning, they were put together in one form, and in the end, they're put together in a different form, right? So you can envision it as taking them apart and putting them back together. Well, there's energy associated with both of those, okay? For this part here, we've already talked about that. We've already said if you take your elements and put them together and make a compound, that's a formation. So this here is a heat of formation. I'm putting it together. This would be a heat of decomposition. So H of decomposition. There we go. Now, if you've watched a few of my other videos, especially the one on heating and cooling curves, we did talk about how if you have exactly the opposite process, then you get exactly the opposite heat. Okay? Think of it like an ice cube. If you have an ice cube and you have to put in, say, 100 joules to melt it into water, well, then if you want to turn it back into an ice cube, you got to take out 100 joules, right? If 100 joules melts it, then taking that 100 joules back should freeze it again. If you have exactly the opposite process, you should have the same number. Now, in the world of heat, we have to be able to keep track. I need to know, is the heat going in or is the heat coming out, right? So we tend to use positives and negatives. So if I'm putting the heat in to melt the ice, that's a positive 100. But if I'm taking it out, it's a negative 100. Okay? Now the reason why that's important is because up here it's a similar situation. Formation and decomposition are opposites. So I've given you a beautiful table of heats of formation, but nobody's ever going to give you a heat of decomposition. Ever. We don't. Because the heat of decomposition is the same as the heat of formation. It's just negative. Because you're doing the exact opposite thing, right? It's just backwards. So all you need is your table of heats of formations, and then you just decide. Do I use them as they are with respect to the products, or do I have to change the sign because they're actually a reactant decomposing? So if we wanted to put all of this together in a nice little formula, what we could say is that the delta H for the reaction is going to be all of the energy required to take apart the products plus all of the energy required to put together the products. Sorry, take apart the reactants, put together the products. So, the amount of energy required to put together the products, that's delta H of formation for the products. The amount of energy required to take apart the reactants, well, we've already said that that's a negative, so that's a negative delta H of formation for the reactants. Sorry if my pictures kind of got overlapped there. Right, so you're doing heats of formations for the products because you're actually forming products, but you're doing negative heats of formation for the reactants because you're actually taking them apart rather than putting them together. So this is the formula that we're going to use for these calculations. Now, some textbooks will write it like this. Some textbooks will put little degree signs here. And all the degree sign says is that the reaction is happening under standard conditions. That when you did this lab or this reaction in the lab, it was 25 degrees and 1 atmosphere of pressure. Just standard, right? If you went into the lab today, the temperature is probably pretty close to 25 degrees and the pressure is pretty close to 1 atmosphere. It does vary a little, but not by a lot. So often we'll put these little degree signs on here to say, hey, we just did this reaction under standard conditions. Okay, sometimes it's there, sometimes it's not. Now the other thing that you have to watch out for, this reaction here is a nice 1 to 1 to 1 to 1, right? You're taking apart 1 sodium hydroxide and 1 HCl, and you're making 1 NaCl and 1 water. But let's say that you're making more than one. If I'm making more than one of these NaCls, let's say I'm going to make 2 of them, then I should get twice as much heat of formation, right? If you're making 2, you should get twice as much heat. Think of it like campfires. If you burn twice as much wood, you should get twice as much heat. So these reactions do tend to have ends in front of them, because if you make more than one of them, you will have to multiply by how many you're making or how many you're taking apart. Okay? But that's where our formula is going to come from. So if we rewrite our little formula over here, we can say that the delta H for this reaction will be N times delta H of the products, formation products, minus N delta H of formation reactants. Now the other thing that may be a bit of an issue here, this heat is not a molar enthalpy change. Okay, this is the enthalpy change for the reaction as it's written. The delta H's of formation, though, are molar. If you think back to the original very first thing we talked about, remember how it was very important that you wanted to make one of these and you wanted to say kilojoules per mole? So for a lot of textbooks, they don't really distinguish between delta H that's just in kilojoules versus a delta H that's in kilojoules per mole, right? They assume that by looking at the units, you can tell them apart. Some textbooks, though, will put a line over the top, and we call that a bar, to show that this actually is per mole, this is per mole, but this is not. This is just for the reaction. Okay, so sometimes we put it in, sometimes we don't. It depends on who's teaching you the course in the textbook. Now, if you wanted to, you could throw all of your numbers into this equation and it'll work for you. I'm a bit more of a spatial organizer. I like to organize my things spatially on the page. So if it was me, I'd draw a little line here because I know that I have to deal with products versus reactants. So let's talk about products versus reactants. So if we bring back our table of values, because I'm going to have to look some stuff up. I know that I am really decomposing the sodium hydroxide, but I also know that it is related to the heat of formation. So I'm just going to write down the heat of formation for each one of the reactants, and I'm going to write down the heats of formation for both products. So for sodium hydroxide, the value is a minus 426.7 kilojoules per mole. If I look up the value for HCl, HCl is way down here. It's a negative 92.3 kilojoules per mole. If I look up the value for sodium chloride, sodium chloride is a minus 411.0 kilojoules per mole. And if I look up the value for water, now you got to be careful of some of these. This is water gas. And you'll notice that in my table, I have water liquid and water gas. And if I was being particularly mean, I'd probably put in water solid as well, because they all have different values. And it would be sort of a, do you think I can trip them up and make them choose the wrong value? So be really careful that you choose the right one. So for water gas, the value is a minus 241.8 kilojoules per mole. Okay, so I've pulled out my values. Now the other thing that the formula says, it says you have to take into consideration how many that you're making or how many that you're decomposing. So for this problem, it's a nice 1 to 1 to 1 to 1. I'm going to make one of these, take apart one. I'm going to take apart one of those. I'm going to take apart one of those, and I'm going to take apart one of those. Now, the main reason why I wanted to show the ones here is purely for the units. When I write this equation and say I have one of these plus one of these giving me one of those and one of those, you can interpret it as literally just one sodium hydroxide in your hand, just one, reacting with one HCl, making one of these and one of those. But if you had just one atom in your hand, atoms are so tiny that you wouldn't be able to see a sodium hydroxide. It'd just be too tiny. So when we talk about these, really we talk about them as you have a mole of sodium hydroxide. Because a mole of sodium hydroxide would be about 40 grams. It would be a little pile of powder in your hand that you'd be able to see. Right? We talk about a mole of HCl, a mole of NaCl, and a mole of water. So when I wrote down all of these ones to multiply, they really should be 1 mole, 1 mole, 1 mole, sorry, that mole kind of got squished, and 1 mole. And for all of them, mole in the numerator and mole in the denominator cancel. So that'll leave me with just units of kilojoules, right? Moles and moles cancel, moles and moles cancel, moles and moles cancel. So that way, in the end, my answer will only be in kilojoules, which is what I want, right? This is a molar enthalpy change. It's going to be per mole, but this is just the energy change for the entire reaction as it's written. So this one will just be in kilojoules. This is how my moles disappear. Now, I do have to do a total, right? I need a total of how much energy is related to the reactants, a total of how much energy is related to the products. So 1 times 426.7 negative plus 1 times 92.3 negative gives me a minus 519.0 kilojoules, right? The moles have canceled. This is the total amount of energy related to the reactants. Now, if we do the same thing for the products, I've got 411.0 negative times 1 plus a negative 241.8 times 1 gives me a value of minus 652.8 kilojoules. And again, all the moles have canceled. Now, if you put them into your formula says find all the heats of formations of the products and multiply by the number of moles. Well, I've done all of that, right? I found the values, I multiplied by the moles. So this is just the minus 652.8 kilojoules. Minus the amount of heats of formation for the reactants times how many you have. Well, I've done that right here. So this would be a minus 519.0 kilojoules. Now, the reason why the negative is here is because this value came from the table of heats of formation. This is the amount of energy needed to form the reactants. But I'm not forming the reactants. I'm taking the reactants apart, right? I am decomposing them. So it has to be the opposite. So that would give me a total amount of energy, minus 652.8, it's already in my calculator, minus 519.0 negative, gives me a value of minus 133.8 kilojoules. If I were to do this reaction, 1 mole of each of these turning into 1 mole of each of those, the amount of energy that I would measure is a minus 133.8 kilojoules. Okay. Now, the first one, we like to talk a fair amount of explanation. It's like, why are we doing it the way we're doing it? Let's see if we can streamline it a bit for B. So in B, I know that moles and moles are going to cancel. And because I'm writing with a fairly large tipped pen, I don't really have a whole lot of room. So because I know the moles are going to cancel, I'm going to pre-cancel them. So I'm just going to say that this is 3 times whatever the value is for Fe2O3 plus 1 times the value of what it is for CO. And when I look them up, I'm going to look them up just as kilojoules, and I'll cancel out the moles as I go. Right? Same thing on the product side. 2 times the value for the Fe3O4 and 1 times the value for the CO2. Okay, so let's move this up a little bit so that way we've got enough room to put in our table so we can look up our values. So, Fe2O3 solid. Fe2O3 solid. That's a negative 824.2. Negative 824.2 kilojoules. right? I left out the per mole because I've already canceled it. Carbon monoxide. Now, remember a little earlier I talked about how the tables will have water, liquid, gas, and solid, and you got to be careful not to mix yourself up. Carbon dioxide and carbon monoxide are the same deal, right? The formulas are virtually the same, and it's really easy to pull the wrong number out. So you do have to be vigilant. So for this one here, I am looking for carbon monoxide. So that's the minus 110.5 kilojoules. Over on this side, we've got Fe3O4. So that's right here. It's minus 118.4 kilojoules. And I got a carbon dioxide, and carbon dioxide is the minus 393.5 kilojoules. Now, obviously, when I made my brackets, I made them a little too small. An important thing in the world of chemistry and all sciences, really, is practice, right? By the time I get to the last problem, my problems will be very, very clean and very efficient, right? I'll know how much space to leave for things. I'll be able to organize things in the optimal way. The more problems you do, the better you get at organizing them on your page, and the easier they'll become for you, right? So the trick here is practice, lots and lots and lots of practice. Okay, so let's add up the reactant side. So I have, now, remember, this is the heat required to make one of those. So if you're making one Fe2O3, that's the amount of heat that goes with it. But I'm not making one, I'm making 3. Well, I guess technically I'm taking apart 3, but there's 3 of them involved, so I need 3 times the heat. Right? Same thing over here. There's 2 Fe3O4s involved, and so I need twice the heat, because this heat only goes with one of them, not 2. Okay, so let's do our multiplication. 3 times 824.2 negative plus 1 times 110.5 negative gives me a total of minus 2,583.1 kilojoules. All right, if we go over here on the product side. On the product side, I've got 2 times 118.4 negative plus 1 times 393.5, also negative, gives me a negative 630.3. Now that don't sound right. I'm pretty sure I forgot my negative sign up here. Maybe. I don't know. When you get a number that you're not quite happy with, check it, right? Because a mistake here is going to cascade into the rest of your problems. So I'm going to try it again. 2 times 108.4 negative plus 393.5 negative, and I get 630.3 again. Okay, so the number is good. For the minute, I was a little unhappy, but I checked it and now I'm feeling better. Now, the other thing is, the formula that we wrote up here in the top, that seems a little excessive, right? That's the formula that I'm working with, but we're chemists. We like to be a bit more streamlined than that. So what we'll often do is just say delta H for the reaction is just products minus reactants, right? Because if you think back to what we had here, I did the whole thing for the products, and then I subtracted off what was there for the reactants. That's essentially what I have here. Find the value for the products, subtract off the reactants. So my products would be minus 630.3 kilojoules minus a minus 2,583.1 kilojoules. So I've already got the minus 630.3 in my calculator, minus a minus 2,583.1 negative equals 1,952.8 kilojoules. And you're done. This is the amount of energy associated with this reaction. Now, one of the questions you may be asked is, so why didn't you just put these chemicals together in a calorimeter and measure the heat? Right? Because these reactions, you could put the chemicals in your calorimeter and measure the heat. Part of the reason is some of these reactions are really slow, and they're so slow that you can't really measure them in a calorimeter easily. Some of the reactions are dangerous, and you don't want to measure them in a calorimeter. The other thing is, when you get positive answers, this means that this is an endothermic reaction. Positive delta H's mean heat goes in. Endothermic reactions tend not to be spontaneous, which means that if you mix the chemicals together, they tend not to actually react, or they react really slowly. Okay, so this reaction may not be one that actually happens in the real world, but for whatever reason, I want to know the amount of heat that goes with it, right? The calculations allow us to do that. All right, let's jump down to the third one, because the third one has another nice little surprise hiding there. At this point, you get the feel for how we're going to set them up, right? We're going to do reactants, we're going to do products. So I've got two H2S's, dihydrogen sulfides, so 2 times. And I have learned my lesson. I've made my brackets a little bit bigger this time. I've got 3 times the oxygen, because there's 3 oxygens. I've got 2 times the water, and I do notice that it's a liquid, so that way I'll look up the right answer. And I got 2 times the SO2s. So if I pull out my table again, okay, so H2S, dihydrogen sulfide, H2S is right here, minus 20.1. Now, technically, it's kilojoules per mole, but the 2 already has moles in it, so I've canceled out my moles in my head. Now, if your teacher requires you to put in your moles here and your kilojoules per mole there and then show the canceling, then you're going to have to do that. But if whoever's asking you to do this is not asking you to actually show your units in the calculation, it's a nice little step. It'll save you a little bit of space. Okay, the next chemical is oxygen, O2. If I look down through my list, I find that O2 is not on the list. That might be a bit of an issue. Let's skip it and come back to it. Okay, liquid water. I've got liquid water. Liquid water is here. So that's a minus 285.8 kilojoules. And I've got my SO2 right here. It's a minus 296.1 kilojoules. Now you'll notice just going from this problem to this one, I got my spacing a little bit better, right? Practice helps. Now there is a reason why O2 is not in my table. Okay? Let's say that I wanted to make some O2 gas. Okay, so I'm going to do heat of formation. I'm going to form some O2 gas. We've already said that if you form something, you have to decide what element you need. So the element that I need to make O2 gas is oxygen, right? You need oxygens to make O2. In the real world, under normal conditions, oxygens like to come as pairs. At room temperature, it's a gas. So if you're going to make oxygen gas from its element, this is the reaction you get. Oxygen gas turning into oxygen gas. And the question you ask yourself is, did you actually do anything here? And the answer is no. It started and ended exactly the same. So the delta H of formation would be 0 because you didn't actually do anything. And it's the reason why the O2 was left off the table. All of the elements are left out of your tables. Like when you go through the table, you would never see Cl2 gas. You would never see Fe solid. You would never see Cu solid, right? All of the elements in the states that they are at room temperature, right? Chlorine is normally a gas, iron's normally a solid, copper is normally a solid. They all have heats of formation of 0. And again, we're chemists. We don't want to waste our time writing things down that we don't need to. So when we build our tables, we often leave the elements out because they have values of 0. So if you're doing a problem and you're looking something up and you can't find it in your table, the first thing that should come through your mind is, oh, wait, is this an element? is this something that has a value of 0? Okay. So for the oxygen, this will be 0 kilojoules. Now, I should come back and point out that the state is very important. Because let's say I wanted to make O2 liquid. If you're going from O2 gas to O2 liquid, that actually is a change. So your delta H of formation would not be 0, right? So if you have things in your table that are like unusual, like you've got iron, but it's a liquid. You have copper, but it's a gas. Those things will have values that are not 0. But if you have the element the way it exists out in the real world, right? If something is normally a gas like oxygen and it is a gas, then that will be a 0. Okay? All right. It's an easy thing, but it does tend to trip people up because when you go looking for it, oftentimes it's not in the table and then you kind of feel stuck. Okay, so now that we have our numbers, just like before, let's multiply them out. So I've got 2 times a negative 20 plus 3 times 0. That would give me a minus 40.2 kilojoules. That's the total for my reactants. Now I am going to need to use my calculator for the products. So that's a 2 times 285.8 negative plus 2 times 296.1 negative. That gives me a minus 1,163.8 kilojoules. Total for the products, total for the reactants. And we said the delta H for this reaction is going to be products minus reactants. Because the products, you're actually making them. So this heat is exactly what I want, the minus 1163.8. But we're not actually forming the reactants, we're decomposing them, the opposite. That's why we throw the negative sign in, right? Because that changes the sign of this number. That's a minus 40.2 kilojoules. And if we haul out our calculator, this number is already in my calculator. So minus a minus 40.2 gives me a minus 1,123.6 kilojoules. And that would be your answer. That's how you use heats of formation to predict the amount of heat associated with a chemical reaction. Now, let's say that we'd like to take this just one step further. What about if you're not given the reaction? Right? In the first 3 problems, I gave you the reaction. Here were all the reactants and products. They were all balanced. Everything was given to you. What about, though, if it's given to you in words? Okay, so now this has really a couple of problems, all kind of stacked on top of each other. The first one is, can you turn the words into chemical formulas? Because you can't do any of this unless you know what the chemicals are. So, gaseous ammonia is burned in oxygen gas to form gaseous nitrogen monoxide and liquid water. Okay, let's talk about ammonia. Ammonia is not the IUPAC name for this chemical. Ammonia is sort of the street name for it, right? If you went to the grocery store and you were looking for some ammonia, you'd be able to find it. If you're looking for it as nitrogen trihydride, you probably won't, right? So ammonia is one of those that we don't usually use its official correct scientific name for. We often just use its street name. And the reason why it's so popular is because ammonia is a weak base. And we like working with weak bases. This actually is our favorite one. So it is worth your while memorizing that ammonia is NH3. Okay, if you're going to be doing some more chemistry besides just this type of problem, it will help you to memorize its formula. Okay, so ammonia is NH3. It is gaseous, so that's G. It is burned in oxygen gas, so that would be oxygen. Now, this is another one of those tricky spots. Even though it said oxygen gas, this is a real-world reaction. And because it's a real-world reaction, you have to think of how does oxygen exist out in the real world? It likes to be diatomic. It likes to come in pairs. So that's an O2, it's a gas. Now, nitrogen monoxide, that's an official IUPAC name. Nitrogen monoxide means one nitrogen, one oxygen. And it is gas. And liquid water. Okay, we're all familiar with water, it's H2O, liquid. So the first step of this problem was transferring or translating written names into chemical names, right? Chemical formulas. The second thing that we have to do here is balance it, because this equation may or may not be balanced. Okay, so I really want to save the space here underneath for doing my reactants versus products delta H's. So if I'm going to balance this thing, let's do it on a separate sheet of paper. So if I count what I have here, I've got 1 nitrogen, I've got 3 hydrogens, I've got 2 oxygens. On this side, I've got 1 nitrogen, I've got 2 hydrogens, and I've got 2 oxygens. So nitrogens balance, reactant to product. Oxygens balance, reactant to product. But the hydrogens are a mess, right? 3 versus 2. Now, it is one of those where you're going to have to change both of them. Think fractions. If I told you that I had something with a denominator of 3, and I had something with a denominator of 2, and I asked you what's the common denominator, you would say, hey, the common denominator is 6. That's what we're going to go with here. In order to make the number of hydrogens at the beginning and the end the same, I'm going to attempt to turn this into 6, and I'm going to attempt to turn this into 6. Okay, so if NH3 has 3 hydrogens, and I would really like to have 6, that means I got to double the whole thing, right? Because 2 times 3 will give me 6. If I want 6 hydrogens here, and I've only got 2, if you put a 3 out in front, 3 times 2 will give you 6. Now, that messes up everything else, right? Because the minute I put the 2 here, it didn't just double the number of hydrogens, it also doubled the number of nitrogens, so I got twice those. Same thing over here, right? When I put the 3 here, it didn't just triple the number of hydrogens to give me 6, it also tripled the number of oxygens. So 3 times 1 is 3 oxygens, plus 1 more is 4. Now, I got my hydrogens working, but now I got to fix the other things. So let's say that we talk about the nitrogen. This side has 2, this side has only 1. If I want to turn this into a 2, I just need to put a 2 in front. Because 2 times the nitrogen gives me 2. But again, it messes with my oxygens, right? Because I now have 2 times 1 here, 3 times 1 here, so I have 5. And in this particular problem, the nitrogens now work, the hydrogens now work, the oxygens don't. And oxygen often causes you problems. Like, oxygen is often difficult. Because on this side I have 5, but over here they come in pairs. Right? There's nothing that I can multiply 2 by that's a whole number to turn it into 5. Right? The best that I can do is put a 2.5 here. Right? 2.5 times 2 would give me 5 oxygens and I'm balanced. Right? Oxygen often, in order to balance something, you'll end up going with like a 0.5. So 1.5, 2.5, 3.5, and you get like a decimal coefficient. But now I have 2.5 times 2 is 5 oxygens on both sides. So we're balanced. When we were doing heats of formation at the very beginning, I said we don't mind having decimal coefficients because we really want to have one of the product. But the only place that we really do that is heats of formation, not in just general reactions, right? This is a general reaction. So for this one here, I really don't want to leave the 2.5. But like I said at the beginning, this is like a math equation. Anything you do to the left, you do to the right, and you're good, right? As long as you do it on both sides, you're okay. To get rid of the 2.5, why don't we double everything? Because if I doubled the 2, I'd get 4. If I doubled the 2.5, I'd get 5. If I doubled the 2, I'd get 4. And if I doubled the 3, I'd get 6. And we're balanced, right? 4 hydrogens to 4 hydrogens. 4 times 3 is 12 hydrogens. 6 times 2 is 12 hydrogens. 4 times 1 oxygen and 6 times 1 oxygen is 10 oxygens. 5 times 2 is 10 oxygens. Right? This is a difficult problem to balance, right? If you go back and took a look at some of the videos on balancing chemical equations, this one would be a difficult one. Okay, so we've spent a lot of time on this problem, but we haven't actually hit the heat part of the problem yet. Like, we finally got it to the point where we can now start looking up our values and find the heat that goes with this reaction. All right, so if I take a look at this, I now have 4 ammonias. I have 5 oxygens. I've got 4 NOs, and I've got 6 liquid waters. And I just have to look up the values. So if I look up ammonia, NH3, that's a minus 46.2 kilojoules. Should be kilojoules per mole, but I've already canceled out the moles. There's oxygen. If I look through my list, there's no oxygen, but then I remember elements with their natural states are zeros, so that's 0 kilojoules. Nitrogen monoxide gas is a positive 90.4. Now that is a little bit unusual because if you look at the table, practically everything is a negative number. There's very few positives, but that one's a positive. And the water liquid would be a minus 285.8 kilojoules. And again, be careful because there's often more than one water. All right, so we'll add up all the reactants, we'll add up all the products. So 4 times 46.2 negative plus 0 gives me a minus 184.8 kilojoules. Over here on the other side, 4 times 90.4 plus 6 times 285.8 negative gives me a minus 1,353.2 kilojoules. And the delta H for this reaction would be products minus the reactants. So a minus 1353.2 kilojoules minus a minus 184.8 kilojoules. And so that would give me, I already got this number in my calculator, minus a minus 184.8. Gives me a minus 1,168.4 kilojoules. And that would be the answer. Now, let's talk about the problems. Often when you're doing a chemistry course, we like to do the problems compartmentalized. Like this particular video was focusing on enthalpies of formation. So what I really wanted you to practice or look at was just this part. How do you find the numbers for the reactants and the products? How do you get the heat for the entire reaction? Okay, and that's typically the way most high school courses are taught. But this is a better example of how chemistry really works. Okay, in chemistry, there's often layers upon layers upon layers, right? There's a bunch of skills that you need. Can you convert words into chemical formulas? Can you balance it? And then once you have the equation, can you do something with it? Okay, so as you learn your topics in chemistry, make sure that you remember them and continue to practice them because they do tend to come back. So I'd like to say thank you for joining me here at Chemistry with Dr. Clark.